Okay, so we're going to be going over these pre-made MATLAB examples dealing with model fitting and various issues therein. So let's just plow through. So remember, there are a couple different types of models, and that'll affect how you fit these models: linear models and linearized models, and various types of nonlinear models. So this first example just deals with in the end, what is a linear regression model, but because we're going to expand the input space, it's actually a linearized model. So the model in the end is a nonlinear function of the input, the x variable. So let's just kind of get more concrete there. So we're going to deal with the simple case of a model that's a function of one variable, x. So here I'm going to generate some random data. So we define some x observations, -20 through 20. That's just 41 different data points, and we're going to simulate some function as that's related to x. So here is just a quadratic function of x. So we have x squared multiplied by some scalar, fine, and then we also have x by itself with some scalar. We have an offset, that's fine, and then we're going to add some noise on top of that result. Here we're just using Gaussian noise with 0 mean, but a standard deviation of 30. So that's going to be our simulated data, so exactly the same dimensions as our x. Let's do a quick look of our data before we will go any further. Do a scatter plot. So now we have 41 measurements and an x and y value, and we want to describe the y value here in terms of x. In other words, we want to fit a model that relates x to y. As you can see, it's almost linear, not quite linear, and that makes sense because we simulated, we know what the underlying function is, and there's only a teeny bit of noise, it looks like, in the data. So now we're going to ignore the fact that we kind of knew the model and just look at the data and try to recover the model given the data. So as I said, this is a linearized model, so we can set it up in terms of these matrices and just use ordinary least squares to fit the model. So the first step is let's prepare that regressor matrix. So the first column will just consist of x squared. So we're going to use, remember, the colon just to make it a big column vector, and we're going to square x, and then we're going to have another column that just has the x variable, and we're going to have this last column that has this implicit column of ones that you need in order to fit a offset parameter in your model. So this is just a three column matrix. So I'm using capital X, don't get confused, the original variable is lowercase x. So now we have this regressor matrix. Let's just look at it as an image. The color map's kind of annoying, so let's change that to just a gray color map. And I'm not sure this tells us that much. I mean, we can see the three regressors in some sense. There's the squaring regressors in the first column, so it goes from high to low to high. The original x values are in the second column, and remember they range from -20 to 20. You can almost see that here. And then the last column is a series of just ones. I guess it would help to have a color bar so we can kind of see what value is what. And because the first column just has huge values, it kind of makes it so we can't really see much in the other columns. But anyway, that's fine. You can also, of course, look at the regressors in a different way. So just do a plots each column as a separate little line, and you can see the squaring column, and the regular x column is green, and the constant is a red. So it all looks good. Close those. Okay, so we prepared our regressor matrix, and we already have our data vector. Our data is just in y. Remember, it's a column vector. Actually, currently it's a row vector, but we can quickly make it a column vector. So and then we need to fit this model. We need to find, in other words, what are the optimal set of weights for each regressor. So some weight times that, plus some weight times that, plus some weight times that, and we want the sum of all of those weighted regressors to closely fit the data in y. And if you remember, we can do this with matrix operations to minimize the squared error between the model fit and the data, and you can just do that in one line here. So this, and the only weird part is I had to make y a column vector to get the matrix multiplication to work right. And so you just issue that command and you already have the optimal weights. So it's a 3x1 set of weights, and we can look at them. And if you remember, this is because I added very little noise, it's very close to what we actually used, right? 1.5, negative 60, and 10, and the estimated weights are very close to that. And they're not exact, again, because we added noise to the data.
Sorry if I missed this, but why does inverting like your inverted your regressors times your x can equal us?
So what you're asking, where does the solution come from? So we kind of went over that in the slide. I mean, there's proofs we could do of it, but okay. So we've already fit our model. We know our weights, and there are just a couple other things I show in this example. So remember, the model fit is a weighted sum of the regressors that we started out with. So we can compute what is the fit of the model just by taking our regressor matrix. So we have 3 regressors, and we have our weights, and if we just multiply x times w, that does the weighted sum for us. So just a matter of matrix multiplication. And that's what I do in this next step. You just multiply the original regressors times the estimated weights, and we get the model fit, which is just 41 numbers. Remember, we have 41 data points. Well, the dimensionality is reversed, but so all the fitting does is tries to make the model fit in these values be similar to these values in terms of squared error. So that's fine, and then we can quantify this using our usual metric of squared error. So just subtract corresponding elements, sum all those residuals, square all those residuals and sum them to get a single number, which we can just look at quickly. Right? It's just going to be some number. And the units, of course, will depend on the units of your data, right? If our data were, this is not very useful, format long. Okay, format long G. Oh, that's better. So our original data units had these, these are very big numbers, so that kind of explains why our squared error is this enormous number, and it's very hard to interpret, and we're going to see later metrics that are easier to interpret. Anyway, so then finally we can just visualize all of this. This is pretty straightforward. Just do a scatter plot of the data as we already did. Let's just start with that, like so. And we want to plot our model fit, right? What is the function that we determine that relates x to y? One subtlety is we have to do some work to actually evaluate out that function for the purposes of plotting. And so the idea is we're just going to pick 100 different values along our x-axis here, and so I just use these commands to find 100 equally spaced values. So remember, axis tells us what our current range is, and this will just pick 100 equally spaced values. Saved it in XX, right? So, and then we want to compute the prediction of the model at those x values, and so we kind of repeat what we already did above. You form these regressors, and then you can just use matrix multiplication to do the weighted sum. And then you can plot. So given all those x coordinates and given all the corresponding y coordinates, we can now plot a line that shows that function. So it looks pretty good. And then we can just label some stuff. That puts x and y, and also puts a little title reporting the squared error. All right. Okay, so again, this was fitting. This was linear fitting, but we actually fit a nonlinear model, and the reason is we put in this little x squared regressor. Okay, so the next example turns to something kind of completely different. Some models you can't write down in a linear form. In other words, you can't write down a column or one column or multiple columns of known regressors. And so for those models that you can't write in that form, we have to use a different technique to fit those models. So in this next example, let me just close all the figures here. We're going to again start with some using data. So we have some x coordinates and we know what the function is. Our function is 5x to the 3.5, and then we add some Gaussian noise on top of that. And then let's quickly take a look at what the data look like. So we're trying to predict y from x, and this is a nonlinear function for sure. All right, so basically there's some setup stuff we have to do before we do the command that will do the fitting for us. The command is, so this uses MATLAB's built-in, it has optimization functions that do, remember the search, you got to search through this space for the set of parameters that minimizes the squared error. And so that's what LSQ curveFit does. So the logic is this routine takes some knobs or parameters that control how it functions. So let me just briefly address what they are. So here, this pairing, so this says use a display that's iter. That just means report to the command window at every iteration some of the aspects of how the fitting's going. This says check for valid. So sometimes if you evaluate a function, you might get nans or crazy values, and this just says check for crazy values and crash and give an error message if it encounters crazy values, which is probably a good idea to have as default. By default, the optimizer will limit how long it runs, but here I'm saying there is no maximum function evaluations, just infinite. You can evaluate as many as you want, and also the number of iterations to kind of step through. So remember, the search process might take 1 or 2 or 10 or 100 steps, and this is saying I'm not setting a maximum number, just do as many as you need to find the solution. Then the last two pairings are tolerances. So one issue in these search processes is knowing when you've found the minimum. So you kind of step around, you're getting close, better and better, but at some point you might want to stop. Suppose it takes you 10,000 iterations, but you're only decreasing your error by like 0.001, then there's some tolerance, that's what TOL stands for, within which it'll decide, oh, it's pretty close, so I'll just stop and that's good enough. So these just give some really small value. Of course, if you want more precise results, you might want to make this e to the -8 or e to the -10 or even smaller. But anyway, these are reasonable default values that we might want to use, so let's just do that. So optimset, you can read the help on that, but it basically just creates a data structure, which we haven't really talked about, but it's a structure that kind of stores all these default values in. And there are a lot of other things that we could change, but let's not worry about those. Okay, anyway, so one other thing we got to set up are bounds. So our two parameters in our model, which I guess I didn't explicitly tell you. So our model is y equals some parameter that we are trying to fit times x, and x is raised to some power, which we're also trying to fit. So a and n here are the free parameters. And depending on what search type you're doing, you can set bounds, acceptable bounds for what values those parameters can take on. And so here I'm going to say a is unbounded, so it can range anywhere from -infinity to infinity, and then n I will bound to be no less than 0. So let me just set up, evaluate these two. And then the last and very important bit is the initial seed. So remember, you have to start somewhere in your search space. And this is important because you may hit local minima, remember? And so it's important to pick reasonable starting points. So here the gain is set to 1 and the exponent n is set to 1 as sort of a reasonable starting point. So that should be pretty straightforward. We're just kind of setting up. We haven't done anything really yet. And the last bit is defining. We have to define this function here that we're going to ask the optimizer to optimize. So this function uses let's call it anonymous functions. So this kind of notation, there's an @ sign and then parentheses. Essentially, this is writing a function, but you don't have to make a separate function file, like a .m file and so forth. And so what this function says is, given two inputs, pp and xx, output this thing. And model fun is defined to be that function. So after you evaluate this line, you have a function that's just stored away in a variable here. And so what this function does, let's go through it. I mean, pp is going to be our parameters, just what I've been calling a and n. So it would be something like this, a 2-parameter thing. And it's saying, given a set of parameters and some x values, evaluate the model that we're assuming we want to fit here. So take the first argument of pp as our gain parameter, and that's out here. That makes sense. And then use the second element of pp as our exponent parameter. So this function will, again, it's like, given a set of parameters that I might have in the search space, and given the x values, generate the prediction for y. That's all this is saying. And the reason we need this is because the optimizer needs to know what is the function. I mean, what function should I evaluate? Okay, so then the thing that does all the work is this final call, and it uses the options, right? These little parameters that we told it about up here. It uses the lower bound and upper bound on the parameters, so it kind of knows which part of the search space to kind of look over. It needs to know the data, sort of the x regressor and the y regressor that we sort of generated up here. It needs to know where to start from, so it's going to start from 1, 1, and that's passed in here. And the last bit it needs is what is the model function. All right, so we can evaluate that and evaluate that, and let's evaluate and see what happens. Okay, so if you remember, we put display to iter, which means that it will display a bunch of stuff to the screen, which is useful information at each iteration. So this took 10 iterations, 1 through 10, and it gives us some information that might be useful. This tells us how many times it evaluated the model, which there's computational cost, so it evaluated a total of 33 times. And then I guess these other, so f of x, well, this column is just the squared error. So apparently the squared error starting at 1, 1 was really high, 400,000, and then eventually it got it down to 1,000. So that's good. And then it stopped apparently at iteration 10, and it says that, well, it tells us the reason why it stopped. So it apparently passed, or the changes were within the tolerance that we set up, so it decided that's good enough. These other columns, don't worry about. This is just how big the steps are in the search space, and as you can see, they got smaller and smaller over time. Okay, so out of all of this, I mean, the whole point, remember, was to figure out what are the optimal values for the parameters, and so it ended up with the gain parameter being 5.4. Remember, that's very close to what we simulated. The gain parameter was 5, and then the exponent ended up with was 3.4, which is pretty close to what we started out with. And then the rest of this is just visualizing. So, right, in our visualization, we want to see the model fit, so we have to call this model fun with the parameters that we found. So remember that that's in params, so we got to use that here and then evaluate it out, and we're going to get something that's the same dimensionality as our data. And then we can just plow through the rest of this, put a scatter plot with the data like that, and then just plot up a line. So plot black line, put some labels on the axes, put a title, and you see that it did a good job fitting that function to the data. All right, any quick questions before we go on to the last one? Yes?
Could you just describe what an iteration is again? So is it
Sure.
like you're basically getting closer and closer to minimizing more error? Is that the idea?
Yeah. Let me bring up that slide. I know it's been a week since that previous slide. It's really just doing, remember this figure. So we started at some initial seed, and each iteration we kind of go down this error surface, and in our specific problem it took some number of iterations, 10 iterations, to get to what it thinks is the local minimum. So yeah, that's all. Each dot here you can think of as an iteration, and it'll take some number of iterations to actually get to the solution.
And this is only the case for nonlinear models, not for linear models.
Right, so for nonlinear models that you are going to fit using optimization, there's all these iteration issues. But if you're talking about the either linear models or these linearized models like we did in the first example, the fitting is just really trivial. It's one line. You don't have to futz with local minima and bounds and these options. But for these, in the optimization case, you do. So
when you assume, you throw in like the model function, you kind of assume that it's an exponential model.
sorry, the model function, you assume it's a what model?
Well, sorry, you assume that you know the nonlinear.
That's right. So the assumption of the model is in this step right here. So in fact, we could do something like, I don't know, do something stupid like fit a linear model. Let's try that. So I just redefined model fun, if you see right there. And I think I should be able to just rerun. Okay, it worked. So everything was the same except I changed that function. In this case, it's a linear model. And notice the squared error was 86,000, which was much higher than the nonlinear model. And in fact, we could, if copy and paste wasn't so difficult, I could easily show you how bad it is. So I could do something like that again, make sure hold is on, plot x versus y with a different color. Hopefully I didn't close my oh, there we go. Nice. So that's the linear fit. I mean, it looks like it worked. It didn't go crazy, and actually for linear models there are no local minima, so that's not going to be an issue. But it's sane. It's always good to check your results of what you get, and it is minimizing some of the error. There are many other lines that would be much worse. But any other questions?
So I mean, how do you choose that? You just guess?
Yeah, essentially you guess or kind of choose one that works well. You can try many different, and then there's the issue of there's going to be model selection issues, to use some jargon, and we'll go over that in later classes. But at this point, you just choose something that works. All right, so that's an example of fitting these nonlinear models with optimization, and then the last example is just a different use of optimization. And so optimization doesn't really have to be for fitting these very specific types of models, and you can kind of use optimization as a generic thing to minimize any error metric or any cost function that you want. So in this last example, we go through a case that is kind of related to what we touched upon in the previous class regarding the fact that the median is really the number that minimizes the sum of the absolute differences to all your data points. So let's just quickly do that. So here I'm just generating 1,000 numbers. It doesn't really matter. So here are my 1,000 numbers. Let's do a quick histogram. Okay, and so the median you might expect is somewhere around 0.2 or something, or 0.1. Okay, so we start with our data, and we're going to figure out the answer to what minimizes the sum of the absolute differences using the MATLAB optimizer. So we're going to set up our options as per usual. In this case, we're not even going to bother with bounds. You don't have to put bounds if you don't want. And we're going to start with the initial seed of 0. It's not the greatest initial seed, but it should be fine. And then the last bit that actually does all the work, or is the hard part, is defining the cost function. So this routine is actually a different call than what we used a second ago. So in the previous example, we used LSQ curve fit. So that kind of stands for least squares curve fit. And there's this other routine, which really is just a wrapper and kind of using the same underlying stuff, LSQ non-lin. And you should read also the help for each of these, but in this case, we don't have to pass x and y. There's not really an x and y. We're just going to pass the thing to minimize. So what is that thing? So this thing takes the vector of parameters. In this case, we really just have one parameter. We're just trying to find the one number that minimizes, or the sum of the absolute differences. So that's pp. And so all this does is subtracts, this is the difference between the data, which is an x, and that parameter, and then you just take the absolute value. So now we have the absolute differences. And then the last thing is we take the square root. And the reason is LSQ non-lin automatically squares the output of cost fun, and but we don't want to minimize the sum of the squared differences. We want to minimize the sum of the absolute differences. So we kind of fake it out by, if we do a square root here, then when LSQ non-lin squares it, we're back to absolute value. So
whatever output you put in, even if it's just like x minus n, you can square that.
it'll automatically always square it. So then the idea is it's going to search over our space of one parameter. So our initial seed was 0, but it'll jiggle that around. It'll then look at the cost function. So here, this is the square root of the differences. It's going to automatically square that and then sum. In the end, the result is it's going to minimize. It's going to find the parameter that minimizes the sum of all the absolute differences. So let's just do that. Oops. Okay, so this is good. So I'm looking at the third column. 0 apparently was 319 as the sum of absolute differences, but it can do better. So it eventually stumbled upon some value, which was that. So it decided 0.239 minimized this cost function that we set up. And if you check what was the median of the data, it's very close, and there is a bit of small difference, and I talk about that briefly in the example. Any questions on that?